All right, I just went through a lot of this recording just talking to nothing because it was not recording. We are going back to a new scenario. I'm not going to rewrite everything. I'm just going to talk it through, okay? Which might be better. All right. So first we did our part 1, right? We had only 10 milliliters of NaOH that was added. And when we went through, we were able to figure out the pH because when we put in the table, this was instead 1, this was 1, so then we had 1.5 times 10 to the minus 3. That's why. We had 1.5 times 10 to the minus 3 OH, or acetic acid, that was left over. So from that amount of acetic acid that dissociated, we were able to figure out our H concentration, which then gave us the pH. This is a little bit different because for this example, we have the same amount of acetic acid and sodium hydroxide that's being added, and all of it is being consumed on this side. The only thing that is forming is the salt, which is 2.5 times 10 to the minus 3. Now, we have some salt that's present, so that means that when it dissociates, we have some conjugate base that's present. So we need to figure out what that conjugate base, what the pH of that is. And so how we do that is we take, first of all, we know that the equilibrium concentration of the conjugate base is 2.5 times 10 to the minus 3 because we had the initial concentration from the salt from here. So that forms here because it completely dissociates. And then we need to figure out the concentration of actual salt, which would be the concentration of conjugate base. That would be 2.5 times 10 to the minus 3 moles divided by the total volume in the solution. The total volume of the solution is here, 25 plus 25, which is 50 milliliters. We then convert to 0.05 molar. And then we realize that we need to write this equation here to solve, because we're trying to figure out the amount of OH, which we could then correlate to H, okay? So we start with conjugate base because conjugate base was formed from the salt that was formed. We add water, and then that gives us the acetic acid and OH. And this is a partial dissociation, so we have to account for that. So partially dissociates, so the change is at minus X, so not all of this gets formed into acetic acid and OH, just a piece of it. So that's minus X, and plus X. So we end up with equilibrium concentrations of 0.05 minus X for the conjugate base, and for X for the acetic acid, and OH we end up with X. Now, in order to solve for OH, we're going to have to use the KB, which is the basic ionization equilibrium constant, because we're talking about OH. So we look up in table 16.3 to find that the KB for base is 5.6 times 10 to the minus 10. So we put that in, and we put in X times X over 0.05 minus X. We're going to make an approximation and assume that this is very small. So then we then solve for X and find out that X is equal to 5.3 times 10 to the minus 6 molar. This X is OH, so this is the OH concentration. Once we have OH concentration, we then can figure out the POH by putting this value into the negative log of this. So negative log of 5.3 times 10 to the minus 6 is equal to something, which then gives us, okay, they skipped some steps, so let me find my calculator. I don't know where it is. Okay, they skipped some steps, and they figured out eventually that the pH is equal to 8.72. Okay? So once we got X is equal to OH. We take the negative log of that to get the POH. We subtract from 14, and we get a pH equal to 8.72. So that's the pH if we have equal amounts of weak acid and weak base. The last example and final example of the day is if we add more base than we have acid again. We got to do that always, right? Yeah. So that changes this. This is scenario 3. Making sure I'm still taping. Okay, 3 to 35. This is 35, right? Which then makes this 3.5 here. So then we start with, again, still 2.5 times 10 to the minus 3. For NaOH, we have 3.5, and we have no salt that's present. The change now is all of the acid is going to be consumed, and we're going to have excess base left over, and we're going to have some salt that shows up too. So still it's minus 2.5. 2.5 times 10 to the minus 3 salt is produced, and we have excess base of 1 times 10 to the minus 3 that shows up down here. So now we have base that fully dissociates to get an OH, and we also have conjugate base as well to make it fun, right? I don't know. So we have a new reaction that we get to write. I'm going to erase this. Okay, now we have NaOH plus salt, not salt, but conjugate base, CH3COO minus, because this fully dissociates to form salt and water. Oh, I already did that. Never mind. Okay, never mind. Great. I'm making this harder. Sorry. We already did that. Okay. So now, okay, we're left with this amount of OH. Oh, and all of this is salt. What we're assuming is whatever we created as far as this conjugate base, concentration is way smaller than the contribution that the OH is going to produce. Because this is a weak conjugate base, this is a super strong base. So we're going to assume that the pH, the POH can be calculated from the amount of base, 1 times 10 to the minus 3, divided by the total volume of solution, which is 60, to then give us a total concentration of base to be 0.0167 molar. So the difference is, yes, we do have some conjugate base that is formed, and it weakly dissociates. And if we went ahead and looked at this reaction, the COO minus plus water to give a little bit of acetic acid plus OH, we could figure out this OH just like we did for